So with this thorough understanding of 2x2 systems, let's now move our attention to a general n by n system and discuss the stability of constant coefficient, linear constant coefficient, homogeneous, n by n systems of first order ODEs. And I'm not going to go through and classify all of the different types of equilibrium points we can have, because in general this is complicated, and you'll see this even if you go through and try and do what we just did for 2x2 systems, for 3x3 systems. However, we can get a basic idea of characterization for stability of systems of the form xi prime is equal to a xi, where xi at some initial condition t naught is equal to xi naught. And recall that we showed the solution of such systems is of the form xi of t for initial condition xi naught is equal to e to the a times t. This is the matrix exponential e to the at matrix multiplied by the initial condition xi naught. And we'll be considering this for systems where the determinant of matrix A is non-zero. So recall that the definition of stability means that the solution xi of t corresponding to an initial condition xi naught is stable on the interval from 0 to infinity, provided that for any positive epsilon, positive tolerance, there exists a positive delta such that if our initial condition xi naught is within delta of the origin, then the size of the solution xi of t corresponding to these initial conditions xi naught stays less than epsilon. Which means that e to the at times xi naught itself has to stay less than epsilon for t positive. We also have that xi of t is unstable if it is not stable in that it is globally asymptotically stable if it is stable and for any initial condition, the limit as t goes to infinity of xi of t comma xi naught is equal to the zero vector. And this globally here just means that it happens for any initial condition, regardless of the initial condition. We can recall that because if the determinant of A is non-zero, the only equilibrium point will be the origin. So we'll really only have one equilibrium point, which can be either stable, unstable, or globally asymptotically stable. And using the condition that, or the solution in terms of a matrix exponential, it's relatively straightforward to go through and show the following theorem and how it relates to the stability conditions relate to the eigenvalues of the matrix A. So if A is a constant n by n matrix, we have that if A has an eigenvalue this means at least one, possibly more, positive real part, then the solution xi of t comma xi naught is unstable. This is something we definitely saw in 2D because with the either whether it be a saddle point or an unstable node, asymptotically stable node, whenever we have a positive real part for an eigenvalue, the solution will shoot away from the origin eventually. For certain initial conditions. The next thing we can say is that if all of the eigenvalues of A with zero real part are simple, which means they have multiplicity 1, then the solution is stable. And this is also something that we noticed in 2D. This corresponds to the centers, where we have distinct complex eigenvalues but with 0 real part. So the solution just oscillates around this equilibrium point, the origin, but never converges to the origin, so it's not asymptotically stable. And the last part of this theorem here is if the eigenvalues of the matrix A all have negative real part, or all of the eigenvalues then the solution is globally asymptotically stable, or converges towards the origin. And a number of different, these are proved in the book. I'm not going to go over the proofs in this lecture. This is example 2.46 in the book if you're interested. This proof is not that out in the book, but they do go over how to kind of sketch it out and do it. It's based on the Putzer algorithm from before. And all of these are kind of related to this definition of stability up here in the matrix exponential and how that interacts with the norm. But the proof of 3 is in our book. Which is the book on advanced ordinary differential equations by Kelly. But just for example, we'll go over 2 separate examples right now to show how to apply this. If you look at xi prime is equal to x prime, y prime, z prime is equal to -2, 1, 0, -1, -2, 0, 0, 0, 1. So if we were to analyze the stability of this system, the determinant of the matrix A in this system is non-zero. So there's one equilibrium point, which is the origin. And the characteristic polynomial the determinant of A minus lambda I, which is going to be -2 minus lambda times the determinant of -2 minus lambda 0, 0, 1 minus lambda minus 1 times the determinant of the matrix -1, 0, 0, 1 minus lambda, which after a little bit of algebra simplifies to lambda squared plus 4 lambda plus 5 times lambda minus 1. And so the eigenvalues where lambda is equal to 1, and lambda 1 is the roots. Lambda 1, lambda 2 are the roots of this equation right here. So negative 2 plus I, lambda 2 is negative 2, or positive 2 plus I, and lambda 3 is equal to 1. You can see that by doing the quadratic formula here. The eigenvalues are where rho of lambda is 0. And this happens. And lambda is equal to negative 4 plus or minus the square root of 4 squared minus 4 times 5 times 4 times 1 times 5 over 2. Which results in negative 2 plus or minus the square root of negative 4 over 2, which is negative 2 plus or minus the square root of I. Oh, this should be negative 2 minus I, negative 2 plus I right here. Well, we have to conclude that the solution xi of t xi naught is unstable because the real part of lambda 3 is equal to 1, which is positive, greater than 0. This is very, very strong. This gives us the ability to tell, in a general sense, what's going on with the solution without even going through of a general invariant system without even going through and solving it. Now, you can still go through and you know how to solve this directly by finding the eigenvectors for lambda 1, lambda 2, and lambda 3, and then plugging into our formula from before, variation of constants formula, using the fundamental solution. But it's really unnecessary if we're just going to talk about the stability of the actual the origin, or the one equilibrium point for the system. Oops, and I just realized I have a slight typo here. This shouldn't be the square root of I, this should just be I itself. Because the square root of negative 4 is 2 times I, divided by 2 is 1. This should just be I. Sorry about that. For a different example, consider the system that we talked about before, and we haven't written I think we've written down the system, but I'll just re-go over it. If we have, say, 2 linear springs, or 3 linear springs, connecting 2 masses, M1 and M2, we'll say the distance from equilibrium of spring 1 is u, of t, and the distance from equilibrium for spring 2 is v of t. This is m1, k1, k2, m2, k3. From Newton's second law, we end up obtaining that for m1 u dot dot is equal to negative cu dot minus the force on m1 from spring 1 plus the force on m1 from spring 2, or the tension, sorry. So this is going to be due to the stretching of U and U alone. The tension due on mass 1 due to spring 2 is going to be V minus U. It's going to be due to the stretching, the difference between V and U, which is the total amount of stretching of spring 2. And Newton's second law for the second spring is going to be negative C V dot minus tension on spring 2, or on mass 2, due to the difference V minus U, and then lastly minus the force due to the stretching V brought about by K3, the tension on M2 from K3, which is just due to V and V alone. We're also assuming a linear friction term. Of the form negative C times the velocity. So the spring tension is Ki times the stretching of the spring, and we have a linear friction term. Any of these can be changed if you want to complexify the model and make it more realistic. But if we make things more complicated, we're going to end up with a nonlinear system. So, for the first equation, we have m1 u dot dot is equal to negative c u dot minus k1 times u plus k2 times v minus u and m2v dot dot is equal to negative cv dot minus k2 times v minus u plus or minus k3 times v. Or we can now rewrite this by introducing a 4-dimensional vector, xi1, xi2, xi3, xi4, where xi1 is just going to be equal to u, xi2 is equal to u dot, or xi1 dot, xi3 is equal to v, and xi4 is equal to xi3 dot, which is v dot. So the system of 4 first-order differential equations that's equivalent to the system of 2 second-order differential equations will be the following system. Xi dot is equal to Xi2 and then Xi2 is equal to 1 over m1. Xi2 dot, I should say, is 1 over m1 negative c Xi2 minus k1 Xi1 plus k2 Xi3 minus Xi1, then Xi4, and then 1 over m2 times negative c Xi4 minus k2 times Xi3 minus Xi1 minus k3 Xi3. Which is equivalent to the system Xi dot is equal to zero, 1, 0, 0, negative k1 plus k2 over m1 negative c over m1 positive k2 over m1 0, 0, 0, 0, 1 k2 over m2 0 negative k2 plus k3 over m2 and negative c over m2 times Xi1, Xi2, Xi3, Xi4, where this is the matrix A. This entire thing is A times Xi. So the solution of this system of 2 first-order ODEs is really equivalent to this system of 2 second-order ODEs, which constant coefficient linear is equivalent to the solution of this first-order homogeneous system of ODEs, which is very, very cool. And after relatively long calculation, for the determinant of a 4x4 matrix, the characteristic polynomial can be shown to be lambda to the 4 plus c over m1 c over m2 times lambda cubed plus k1 plus k2 over m1 plus k2 plus k3 over m2 times lambda squared plus c over m1 m2 times k1 plus 2k2 plus k3 times lambda plus k1 times k2 plus k1 times k3 plus k2 times k3 all over m1 times m2. And I'm not going to go through and do, try to solve for the roots of this characteristic polynomial in general, because it'd be way too long. Even this calculation takes a little bit of time to get through. But the idea is that for maybe a specific example, we can go through and talk about what the stability of solutions to the system are going to be. So we'll take that very specific example. C equals K1 equals K2 equals K3 equals M1 equals M2. All of these values equal to 1. And when this happens, you get that row of lambda is lambda to the 4th plus 2 lambda cubed plus 5 lambda squared plus 4 lambda plus 3, which is lambda squared plus lambda plus 1 times lambda squared plus lambda plus 3. This polynomial factors to this quadratic or quartic polynomial factors to the multiplication of these two quadratics right here. And so the zeros of this characteristic polynomial is actually relatively easy to calculate. We can go through with the quadratic formula and get the two roots of this equation, lambda 1 and lambda 2, are given by negative 1/2 minus the square root of 3 over 2 times I, and lambda 2 is negative 1/2 plus the square root of 3 over 2 times I. And then, just like we can go through and get the two roots of this polynomial right here, we can go through and get lambda 3 and lambda 4. Lambda 3 will be negative 1/2 minus the square root of 11 over 2 times I. And lambda 4 will be negative 1/2 plus the square root of 11 over 2 times I. So we have 4 complex eigenvalues. Each with the real part of the eigenvalue less than 0, and they're actually equal, negative 1/2. And therefore, our solution will be asymptotically stable. Specifically, we'll say actually it's globally asymptotically stable. Due to the fact that each one of the eigenvalues is negative. And just like before as well, it's possible to go through and get the eigenvectors and the actual solution. If you want the actual solution, we call alpha 1 negative 1/2. We call beta 1 square root of 3 over 2. And we do the same thing for lambda 3 and lambda 4. We'll call alpha 2 negative 1/2 and beta 2 square root of 11 over 2. We'll put this to good use. If you go through and calculate the eigenvectors, for lambda 1, the eigenvector becomes, that you end up solving for, will be 1, negative 1/2, 1, negative 1/2, minus I times 0 square root of 3 over 2, 0 root 3 over 2. And for lambda 2, we're going to get in the same expression, only with the positive. It's called the complex conjugate of this value. So we'll call this vector A1 and this vector A2. And likewise, you shouldn't be surprised that when you go through and do the eigenvectors for lambda 4, lambda 3, and lambda 4, you get something very, very, very similar. So similar, in fact, I will just copy this over right here. The eigenvector corresponding to lambda 3, we'll call lambda 3. And this becomes square root of 11 over 2 here, square root of 11 over 2. But because alpha 1 is equal to alpha 2, this is the same. And then same thing for lambda 4, only with a positive value here. And so when you want to go through and get the actual real solution for this system right here, you have to go through and construct 4 real linearly independent solutions for your fundamental solutions matrix, and directly, in the exact same manner to how we did it before for 2x2 systems. You'll get that phi1 is A1 cosine of beta 1 times t minus b1 sine of beta 1 times t times e to the alpha 1t. Phi2 ends up being A1 sine of beta 1 times t plus b1 cosine of beta 1 times t e to the alpha 1 times t. Phi3 is A2 cosine of beta 2 times t minus b2 times sine of beta 2 times t e to the alpha 2 times t. And phi4 is A2 sine of beta 2 times t plus b1 cosine of beta 2 times t times e to the alpha 2 times t. And the fundamental solutions matrix then is just the matrix composed with phi1, phi2, phi3, and phi4 as its columns. And the general solution to the problem will be phi of t times phi of t naught inverse xi naught. Where, by the way, for this problem, this is e to the a times t. This matrix is the same thing as the exponential matrix e to the at for these chosen values of k1, k2, k3, m1, m2, and c, which is very, very cool. But the main point here is that without going through and doing the solution procedure, you can classify the stability of solutions.